Hello everyone and welcome to lecture number 25. My name is Arash Salemi and I'm working with Professor Anand Agarwal at the Department of Electrical and Computer Engineering at The Ohio State University. First of all, I'd like to thank ONR for founding this lecture series on course on silicon and wideband gap power devices. Also, I want to thank Professor Woon-Jae Song at Sunny Poly for sharing some information with us for preparing these slides. In the previous lecture, I explained how can we form all these fingers with different doping concentration in order to make the N plus source, P plus, P well, JFET, and so on. But one thing that is so important, as I mentioned, the JPS as well, after the ion implantation, we need to activate all these dopants in order to contribute electrically in the device. For this case, we need to anneal the sample, and as I mentioned in the JBS lecture, we need a cap layer before annealing. So for making cap layer before the annealing, we can coat the sample with, for example, photoresist, and then anneal it at higher temperature in order to make a graphite cap layer. So in this case, we need, for example, 4 micrometers graphite cap layer over the sample. And then by this cap layer, we can use high temperature annealing, argon ambient 1700 degrees C for 30 minutes in order to activate all these dopants. And after the activation, we can remove this cap layer, carbon cap layer, by oxygen plasma. The next step is oxide deposition. We can deposit the oxide, but after all this implantation, and normally we have bad surface morphology on the surface. So in order to improve the surface morphology, we can use sacrificial oxidation. In this case, we grow oxide, thermal oxide on the surface at high temperature, and then remove this oxide by buffer HF or HF. So, for example, we can have a 20 nanometer sacrificial oxidation, and then by buffer HF we can remove it, and now we can deposit oxide, 50 nanometer dry oxide growth at 1200 degrees C. And after the oxide deposition, we have post-annealing at 1200 degrees C, first in argon ambient for 1 hour, and then NO ambient for 2 hours. This step, passivation, actually is very, very important and critical for these devices in order to achieve a better and higher channel mobility. Otherwise, we'll have a lot of scattering at the surface, and then the mobility, channel mobility, will decrease. So NO is being used in order to passivate the dangling bonds at the surface. Other gases such as N2O or N2O can be used as well, but NO annealing has better result for silicon carbide devices. After the passivation, then we need to grow polysilicon over the oxide. In this case, we can deposit 500 nanometers polysilicon utilizing LPCVD, low pressure chemical vapor deposition. And then we can dope it with phosphorus over the oxide. And now we need to form the polysilicon in order to have the gate poly over the gate. So here is the channel, right? So the gate would be over here on the channel between the N plus source and JFET, in the left hand side of this cell and right hand side of another cell. For this step, polysilicon can be etched utilizing a photoresist mask. So we coat the sample with photoresist using lithography, a mask, exposing and developing. Then we have suitable mask, and then we can dry etch the polysilicon, and after that we can remove the photoresist by oxygen plasma or acetone. Now let's look at the gate poly. As you can see here, the right hand side is the whole device. I zoomed this box to here, so we have this gate pad over here and all these fingers. And if you look at this box, we have 3.3 micrometers distance between the fingers with a width of 4 micrometers. So here we have 4 micrometer gate poly or polysilicon over this source in channel JFET channel, and here is the source. This is actually a combination of P well and plus source, P plus and gate poly all together. So let's look at this part. We have the gate poly over here, 4 micrometers, similar to this cross-sectional view. So 0.5 micrometer, 0.5 micrometer, we have the overlap of the N plus source. This part is so important, the overlap. Suppose that we don't have any overlap, then if we have a misaligning, for example, suppose that we have 1 micrometer of misaligning to the right hand side, then the polysilicon could be a start from this point to the right hand side. In this case, we don't have any gate over the channel, and if we don't have any gate over the channel, it means that we don't have any current in the left hand side. This overlap actually relates on the resolution of the lithography step that you're using. If you, for example, using a stepper with 0.5 micrometer resolution, then you need at least 0.5 micrometer overlayer here, as I mentioned. Here we can see P well and plus source, P plus and gate poly, but at the periphery of the device. So as you remember, we have a wide region of P plus, 55 micrometer width, in order to have a rounding corners. Then over that, with 48 micrometer width, we have also the gate or polysilicon over the P plus. And in the left hand side, for sure, we have the active area in the middle part of the device. After the gate poly and forming the gate poly, we need to deposit oxide over them. So 1 micrometer silicon dioxide can be deposited by PECVD, and then by wet oxide growth at 950 degrees C for 1 hour, we are doing the densification. Again, we are not growing any actually oxide. The growth rate is negligible. We are just densify the oxide that we have deposited in order to have a better quality. And over the oxide, silicon dioxide, we are depositing 200 nanometer silicon nitride by LPCVD in order to have a suitable moisture barrier. Mask number 7 is Ohmic metal over the source, and also P plus over here and here. For this step, for sure we need a photolithography, coating a sample with photoresist, exposing, developing, and after that we can dry the oxide, dry edge of the oxide, silicon nitride and silicon dioxide, utilizing this photoresist mask. And then we have this opening windows for depositing nickel. But one thing is so important: when you etch the oxide and reach to the silicon carbide, you need to put the sample as soon as possible in the evaporator. Otherwise, silicon dioxide will grow on the surface, and then we are putting or depositing nickel or the oxide instead of silicon carbide. So native oxide is so important to be prevented. So after putting the sample in the evaporator, we can deposit 100 nanometer nickel, and then we can use RTA or rapid thermal annealing at 600 degrees C. One thing that is so important over here is actually we are depositing nickel everywhere, right? Over the silicon carbide surface and also over this oxide, silicon nitride here. When we are doing the rapid thermal annealing at 600 degrees C, this nickel make a nickel silicide with the silicon carbide surface, at the surface of the silicon carbide. But there is no reaction between nickel and silicon nitride or silicon dioxide over here. So, if we use, for example, Piranha, we can remove the nickel over the silicon nitride easily, but nickel silicide cannot be removed. So here we are removing unsilicide metal on the oxide, and also we have nickel silicide on the silicon carbide. However, 600 degrees C is not enough temperature in order to have a good ohmic contact. In this lecture, in this paper, we showed that at 600 degrees C we have a peak of nickel silicide, but the intensity of this peak is not enough to have a good ohmic contact. So now, after removing the unsilicide part of the nickel, we can have the second step annealing. So here is the first step annealing at 600 degrees C. But after removing the unsilicide part, we can have the annealing or the second step annealing at higher temperature, 900 or 950 or even 1000 degrees C, in order to increase the intensity of the nickel silicide. And when the intensity of the nickel silicide is increased, it means that we have a better good ohmic contact and lower resistivity. I encourage you to read this paper that we published at KTH in Sweden. Here is mask layout, ohmic metal. As I talked, we have the nickel in the active area. All fingers are in parallel. Then we have 2.3 micrometers width of these nickels with a distance or gap between them is 5 micrometer. As you can see also here. This is a combination of mask layout between gate poly and ohmic metal. So here in the zoom part, we have all these gate poly and nickel metals with 4 micrometers and 2.3 micrometers. 2.3 micrometers is the nickel over here, and 4 micrometer is the width of 10 plus polysilicon over here. And as I mentioned, we have it actually 0.5 micrometer distance, 0.5 micrometer distance between the gate poly and ohmic metal. Next step is backside ohmic metal in order to have a good ohmic contact at the backside. So in this case, we are coating the top side with a photoresist, and then using oxide wet etching in order to remove all native oxides on the backside. Then after that, we need to remove the photoresist as well, and then deposit 140 nanometer nickel at the backside. Then by RTA, rapid thermal annealing, at 950 degrees C in N2 ambient for 1 minute, we will have a good ohmic contact by making a nickel silicide on the back side. Mask number 8 is the gate runner. It cannot be seen in the cross-sectional view. So here is the mask from the top side. So here is the gate pad, and then we have a gate runner in the periphery. So in this case, actually we are opening the oxide or making via for the gate pad area. So you see a combination of gate poly and polygate together. Here is the gate runner at the middle. So again, we are just opening the oxide because we have oxide everywhere. We are just opening the window for these gate runners. 10 micrometers width here, 10 micrometer width over here, and then 28 micrometers width in the left hand side. So now we have the overlayer metal. As I mentioned, 4 micrometer thick aluminum can be used as a top metal in order to have a good current spreading. So in this case, we are sputtering aluminum, 4 micrometer aluminum sputtering. Then by using this photoresist and lithography, we can use the aluminum wet etching in order to etch this part of the aluminum that we don't need it. And then by photoresist stripping, we can remove the photoresist and have aluminum over the gate and nickel ohmic contacts. Here is the mask. Here is the pad, a gate pad and source pad, and as you can see, all these corners have been rounded properly, and the distance between the source pad and gate pad is 15 micrometers. So here is aluminum or the gate and nickel, and here is the aluminum in the periphery for the gate runners that we actually etch the oxide and reach the gate poly, and then we have the aluminum. Here also you can see the aluminum here and here, the P+ and overlayer metal. And then we have the gate poly and overlayer metal all together. Here is the combination of gate poly, gate runner, and overlayer metal. So you see here is the gate runner that we opened the oxide, reached to the polysilicon, and over that we have this aluminum over the gate runner with an overlayer of 5 micrometers in the right hand side and 5 micrometers in the left hand side, in order to be sure that aluminum is connected to the gate poly here. And again, as I mentioned, we have 15 micrometers distance between the gate runners at the periphery and the aluminum on the source pad. So finally, we have polyimide, 7 micrometer polyimide, in order to have a dielectric isolation. And here we are just coating the material, the sample, a 7 micrometer polyimide. Then by utilizing photoresist, lithography, photoresist, exposing, developing, then we can use this photoresist as a mask in order to dry etching of polyimide. And here is the sample after dry etching, and then we can easily remove the photoresist by stripping oxygen plus more acetone. Here you see the mask layout from the top side, gate pad and source pad, and here is the distance, 45 micrometers distance between them. And the gate pad size is 206 micrometers by 263 micrometers. So this is the size of the gate pad. And all these corners, as you can see, have been properly rounded. The next step is backside overlayer metal in order to have a good current spreading on the backside as well. As I mentioned in the previous lecture, in this case we can deposit a stack layer of or titanium, nickel, and silver with a stack ratio of 50, 300, and 100 nanometers. So by this, actually, I explained all these masks, 10 masks from the alignment mark, JFET implantation, P-well, M+ source, and P+, and then activation or activating all these doping concentrations or dopants, and then gate poly, Ohmic metal, gate runner, overlayer metal, and polyimide. And here is the all masks together for a device with 2 by 1 millimeter square. You can see the gate pad, the source pad at the middle with 46 guard rings, and then we have the channel stop, M+ channel stop at the periphery of the device. Thank you very much for your attention.